Hi everyone, I'd like to welcome you to Chapter 7, and in this chapter what we're going to do is we're going to develop a lot of new techniques of integration that will let us greatly broaden the library of functions that we can find antiderivatives of. So the big thing to note about what we've studied so far is that we used our knowledge of derivatives to come up with ways of looking at antiderivatives. So what we've learned so far are things like the table integrals. And the table integrals come from table derivatives. What do I mean by table derivatives? Well, it's the case that if you know a differentiation rule, say d by dx of the sine of x is equal to the cosine of x, then automatically you get an integration rule for that. If cosine is the derivative of sine, then sine must be the antiderivative of the cosine. So if I know a differentiation rule, I can always pair it up with an integration rule. The more sophisticated rule that we developed is called U substitution. And U substitution is related to the chain rule. So the chain rule says that d by dx of f of g is equal to f prime of g times g prime. And its associated integration rule said that the integral of f prime of g times g is equal to f of g. That's where the U substitution actually came from. U was equal to g, and U prime is equal to g prime. So on the one hand, we have the chain rule. On the other hand, we have U substitution. What we're going to do today is we're going to develop the opposite integration rule for the product rule. So remember that the product rule says that if you have a derivative of a product of functions, that you calculate that by doing f prime g plus f g prime. The derivative of a product is the derivative of the first function times the second, plus the first function times the derivative of the second. And what I'm going to do is I'm going to try to reverse this into an integration rule. And not just an integration rule, but one that will allow us to compute integrals that we haven't had access to before. Okay, so here's where we start. We're going to split this integral up into pieces. F g is equal to the integral of f prime g dx plus the integral of f g prime dx. I can do that because the integral is linear, so I can split it across this sum into two pieces. So we're going to take this expression and we're going to isolate one of the integrals. F g minus the integral of f g prime dx is equal to the integral of f prime g dx. And you might ask, why did I do that? What, have I really gained anything by making this sort of algebraic move? And the answer is yes. And the reason is, if you look at the equation, you can see that on the right-hand side, we have the integral, one integral of f prime g, and we figured out a way where we can replace that integral with a different integral, the integral of f g prime. And sometimes the integral of f g prime is actually easier to solve than the integral of f prime g. A more typical notation here is to let u be equal to f, and then its differential du is equal to f prime dx, and v be equal to g, and its differential form is dv is equal to g prime dx. And with those substitutions, what you end up is the integration by parts equation. uv minus the integral of v du is equal to the integral of u dv. And this formula is the basis of integration by parts. The reason we call it integration by parts is because when we use the formula, this substitution we make here, where we pick a u and take its derivative, and we pick a dv and take its integral, means that we're dealing with these two pieces separately. What we're going to do now is we're going to take this equation and show how it can be used to calculate integrals that we otherwise can't use any sort of substitution on and don't appear as table integrals. So we'll start by remembering the formula, which is that the integral of u dv is equal to uv minus the integral of v du. So now let's see how this works in application. Let's suppose that I want to compute the integral of x times e to the x dx. Now it's very easy to compute the derivative of x e to the x, but I'm not asking for a derivative, I'm asking for an integral. And this is a product of functions. Products of functions typically are very hard to do. And there's not an obvious u substitution here, because if you let u be x, you just end up with the same integral you started with. And if you let u be e to the x, then there's not an obvious way of changing an x into something involving u. So we're going to use integration by parts here. And the big key is that I notice that the x, if I take its derivative, will disappear. So I'm going to let u be equal to x. And I'm going to find du, which is 1 dx. So u is one of the objects that I pick. I picked the object u. That's this part of the integral. So notice what I did here is I picked the u from this formula. Everything that's left over must be the dv. So dv must be equal to e to the x dx. Now, if you've done this correctly, or the problem can be solved using integration by parts, then whatever you've picked for your dv here is something you actually know how to integrate. So if I need, in the final formula, I'm going to need v's. But I started with a dv. So I have dv here, and I want to get v, so I integrate. Well, what is the integral of e to the x? It's just e to the x. You don't need the plus c in this case because that actually doesn't play a role in the formula. You notice that this formula still has indefinite integrals in it. So when we remove all the integrals in the end, that's where the plus c will be introduced. So how do we use the formula? Well, if this is u and this is dv, so there's dv and here's u, then I can replace that integral with the u, which was x, times v, which was e to the x. So this is u and v, minus the integral of v times du. And you should notice that what you've done here is you've taken this integral that we have no idea how to solve, and we've replaced it with a more complicated expression, but this integral is already done. And this integral is one I know how to do. So all of this is equal to x e to the x minus e to the x plus c, because the antiderivative of e to the x is e to the x. And so this is the answer for that integral. So the idea here is that I've taken this integral I didn't know how to solve, and I've replaced it with an integral I do know how to solve, and that is what lets me get to the actual antiderivative expression at the end. So the art in integration by parts questions is writing down a problem and then choosing what the u and what the dv should be so that you can construct this little table and apply this formula to it. This is a technique that's much easier to learn through lots of practice. So I'm going to try to show another example here so we can see the sorts of things that could happen. So suppose instead that I had something like the integral of x squared e to the x dx. When you're looking at an integral and you think it might be integration by parts, one of the first things you should look at is one of these functions going to disappear if I differentiate it enough times? And the answer here is yes. X squared, if you differentiate it twice, will go away. So I'm thinking because I'm going to differentiate the x squared twice, I'm going to have to use integration by parts twice. And we'll see if that plays out in practice. I'm going to proceed by parts. It's a good idea to indicate what technique you're using, because by the time we're done with chapter 7, we're going to know 6 or 7 different ways of attacking integrals. So I'm going to proceed by parts, and I'm going to tell you what I'm choosing for my u and my dv. I'm going to let u equal x squared, and I'm going to let dv be equal to e to the x dx. So this part is u, and this part is dv. du is 2x dx. And v, remember, you get from dv to v by integration, e to the x. The formula says that this integral should be equal to uv minus the integral of v du. So let's just substitute in and see what we get. Well, u times v is x squared e to the x. And the integral of v du, well, that's these two things multiplied together. So we get the integral of 2x e to the x dx. Now the problem is this integral is still not one that I know how to solve because there's this x inside here. Remember that in the last example, I can do the integral of x e to the x because I can use integration by parts. So we're going to apply integration by parts a second time so that we can turn this integral into one that we know how to solve. Let u be equal to 2x. And let dv be equal to everything that's left over, which is e to the x dx. The derivative of 2x is 2. And the integral of e to the x is e to the x. And now I can use the same exact formula again, but on this integral. So this is equal to x squared e to the x minus, and that entire integral is going to be replaced by the integration by parts formula. So I'm going to get uv, which is 2x e to the x, minus the integral of v du, which is the integral of 2e to the x dx. And now look, I've arrived at an integral that's basic. I know the integral of e to the x. So I can finish the problem by writing x squared e to the x minus 2x e to the x plus 2e to the x plus c. Now you might wonder where this plus sign came from. Remember, this negative out here, it got distributed to both of the terms inside. So that's one type of problem that we get access to with integration by parts. Integration by parts is a lot more powerful than just a tool for using polynomials times functions. We can use it to attack integrals where we don't have any idea how to proceed otherwise. So one obvious example here would be something like the integral of the natural log of x dx. So there is no substitution to make here. And I guess I could guess a function that has the natural log of x as a derivative, but that's actually sort of difficult to start with a function and take its derivative and try to figure out what I need to start with so that the right things cancel so that the natural log falls out in the end. So I'm going to use integration by parts instead. And remember that when you're doing integration by parts, you need a piece that you can take the derivative of, and more importantly, a piece that you can take the integral of. So I need to pick a u and a dv. Well, it wouldn't do me any good to choose the natural log of x as the dv because I don't know its integral. So I'm going to let u equal the log of x. I do know how to take its derivative. And then dv, well, that's just what's left over, which is dx. Well, that's easy to integrate. So du is equal to 1 over x dx. And v, well, the integral of dx is just x. The formula says that this is supposed to be equal to uv minus the integral of v du. So substituting in, what I get is u times v, which is x times the natural log of x, minus the integral of v du. Well, x times 1 over x is 1. And I know the integral of 1, it's x. And so there is the integral of the natural logarithm. And as far as I know, other than guessing, this is the only way to derive this. Another thing that can happen is sometimes we could be taking integrals by parts and nothing ever simplifies, but we end up getting the same integral back again that we started with, in which case we can solve the integral using algebra. That might sound kind of confusing, so let me show you what I mean. If I start with the integral of e to the x sine x dx. Now it might not be obvious that this should be by parts. Everything I've done up to now, I try to choose the u value so that when I take its derivative, it gets simpler. But the problem is e to the x will stay e to the x no matter how many times I take its derivative. And the sine of x, its derivative is cosine, and the derivative of that is sine again. So you get this repeating pattern that you're going to get out of integration by parts. And it might not seem like that's a productive strategy to take. But let's actually try this. We're going to do integration by parts twice, and we're going to look at what we get when we're finished doing that. Here, in a problem like this, it doesn't really matter which the u you pick and which is the dv, because I know integrals and derivatives for both of these forever. I'm a lot more comfortable taking derivatives of trig functions than integrals because I make fewer sign mistakes that way. So I'm going to let my u be equal to the sine of x, and I'll let dv be equal to e to the x because that's easy to integrate. So u is equal to the sine of x, and dv is equal to e to the x dx. I need a derivative of u and an integral of dv, so du is equal to the cosine of x dx, and v is just e to the x. And now the formula says that this integral can be replaced by uv minus the integral of v du. Substituting in, what you get is e to the x sine x minus the integral of v du, e to the x cosine x dx. And you think, well, I haven't really made this problem any better because e to the x cosine x is just as hard to integrate as e to the x sine x is. But bear with me. Let's try one more time. So let u be equal to the cosine of x, so that du is equal to minus the sine of x dx. And we'll let dv be equal to e to the x dx, so that v is e to the x. Let's substitute again, just into that second integral, and we're going to get e to the x sine x minus, okay, all of this gets replaced with uv minus v du, so there's uv, minus the integral of v du, And I'm going to write this out in full form here so I can show you exactly what we've got. Remember that this chain of equalities here has this on the left-hand side. So this thing was what we started with, the integral of e to the x sine x dx. And what we've arrived at on the right-hand side is this giant expression, which looks like this. E to the x sine x minus e to the x cosine x minus the integral of e to the x sine of x dx. And look, this thing right here, which is the unknown, is on both sides of the equation. So I could just solve for it. This almost feels like cheating every time I do it, because it's like I didn't even integrate. I have two integrals, one each on both sides of the equation. I'm just going to treat that whole integral like it's a variable, and I'm going to solve for it using algebra. Some people have an easier time conceptualizing this if they replace the integral that they're looking for with an I. If you replace the integrals with i's, what you're going to get is I is equal to e to the x sine x minus e to the x cosine of x minus I. After all, I is just some unknown variable, right? It's the integral I'm solving for, and that integral is equal to some function, presumably. So let's find out the functions it's equal to. So I can add I to both sides, and I'll get 2I is equal to e to the x sine x minus e to the x cosine of x. And so I is just, I'm going to put a plus c in because these are all indefinite integrals and I haven't picked it up otherwise. But what was I equal to? Well, I was the integral of e to the x sine of x dx. And notice that without actually integrating this, by playing this game with integration by parts, I've come up with an expression that actually is the antiderivative. These problems are amusing for a mathematician. I always enjoyed them as a student. I hope it's not mysterious, the idea here that we've just used this application of a formula so that we can put a variable on both sides that we can solve for. The last thing we need to talk about is what do we do when we have a definite integral? So with a definite integral, I think that the easiest conceptual approach is to do the indefinite integral first, and then at the very end of the problem, apply the fundamental theorem of calculus by plugging the limits of integration in. So what do I mean by that? I mean that this could be replaced with the integral, it's not equal to, so we're going to pretend that there's this wall over here. And we don't want to mix things on either side of the wall, because on this side we have definite integrals, which are numbers, and on this side we have antiderivatives, which are functions, and those don't mix. Okay, so I'm going to solve the indefinite problem over here, and then I'm going to pull it back over to the other side to finish the definite problem. Don't want to lie to your math professor. We showed earlier that the integral of x e to the x dx, if we let u equal x and dv be e to the x dx, that this is equal to uv minus the integral of v du, which is x e to the x minus e to the x plus c. So this is the antiderivative that solves this indefinite equation. But remember that what the fundamental theorem of calculus is having you do is find an antiderivative and then plug these numbers in. So this is how I'm going to do the evaluation. I found the antiderivative over here, and now I'm going to write this as x e to the x minus e to the x plus c evaluated from 0 to 1. The plus c isn't strictly necessary because you're going to take this and then subtract it, so you get c minus c, which is equal to 0. And what you're going to be left with is this expression with 1 plugged in, which is 1 e to the 1 minus e to the 1 plus c, minus that same expression with 0 plugged in, which is 0 e to the 0 minus e to the 0 plus c. And these cancel into a 0, and the c's cancel out, and what you're left with is minus e to the 0, which is 1. What did we learn? What are the techniques that we've developed here? The upshot is I need to know that if I'm looking at an integral of the form the integral of u dv, that by making the right substitutions, I can rewrite this as uv minus the integral of v du. And we learned 4 different cases that this rule applies in. The first is that you have a function that disappears eventually if we take a derivative. Okay. The second is that we have a product of functions where the functions rotate around each other in that cyclic way, like the e to the x sine x problem. A product of functions that give a pattern in the u dv steps. The example here was something like x e to the x, because the x will disappear if you take derivatives long enough. Here it was examples like e to the x cosine of x, because if you keep taking derivatives of e to the x and integrals of cosine of x, eventually you're going to end up with the same integral that you started with. The third case is weird ones, trick cases, like the natural log of x. So the third case is when nothing else works. So there is the example, the integral of the natural log of x dx. And the fourth case was just definite integrals. And to do definite integrals, you just do 1, 2, or 3 first, and then do f of b minus f of a. So in the next video, we'll do some examples of these types of equations, and this is one that you really need to practice to get a lot of. And in the example section, I'll show you a faster way of writing down the UDV parts called the table method. All right, see you in the next video.